Hi again. We now start the last module in this course where we consider spatial clustering explicitly. And this will be organized in 3 lectures. In the first one, I just cover some tricks, so to speak, on how to spatialize classic clustering methods. And then the next 2 lectures are devoted to specific spatially constrained clustering methods, either based on hierarchical clustering or based on partitioning clustering. So I'll start with some basic principles. What is the problem and what are some ad hoc solutions, and then go over 3 ways to spatialize classic cluster methods. Okay, what is the problem? The problem is that in spatial clustering, we want to group objects that are actually contiguous, that border each other. So we want to create new spatial aggregate areal units and make sure that the units that we combine are actually together spatially. And that is the same tension that we've talked about many times before in the context of spatial autocorrelation, namely the tension between attribute similarity, so the grouping of similar observations based on pure variables, and locational similarity, namely a grouping of only observations that are spatially contiguous, that are bordering each other. So this tension between attribute similarity and locational similarity is central to the concept of spatial autocorrelation. It's also central to the concept of spatially constrained clusters. And the solutions to this problem have been around under a number of different terms. They've been developed in operations research, in machine learning, in geography. They're known as regionalization. A special case is redistricting, spatially constrained clustering, contiguity constrained clustering, clustering under connectivity constraints. It's all about the same thing. How do we group similar objects, which is what we've been doing all along in this clustering analysis, and make sure that they are also spatially contiguous? So we have a conflict, as I mentioned. We have, in classic clustering, the locational attributes or the locations of the observations are not taken into account. And classic clustering only focuses on maximizing within group similarity or between group dissimilarity. We saw a slight exception of this when we discussed spectral clustering, but still, once the observations were transformed to the eigenvectors, or the slightly transformed, rescaled eigenvectors, I should say, then it's still the same thing again. So that's all about grouping, minimizing the divergence, so to speak, of the attributes within the same cluster. But then spatial similarity would focus only on location. And in addition, so these are the 2 tensions, these are the 2 objectives that kind of fight against each other. And then we have another one that we could bring into play, but we won't actually do that, which has to do with the shape of the resulting clusters. In other words, spatially contiguous clusters could be long strings of units that are connected, or they have to be somewhat compact. And so here again, we have an additional set of considerations to bring into the picture. Early on in the literature, a number of ad hoc indirect approaches were suggested, essentially starting with a standard clustering algorithm, either hierarchical, k-means, or something like that, and then, quote-unquote, fixing it. In other words, if you end up with, say, k6 clusters, but the units are not contiguous, then you increase k to make sure that each entity consists only of contiguous units, or you start moving units around to make sure that they are contiguous. And the problem is, first of all, this only works for smallish data sets because it's a manual procedure. it also breaks the whole point of the K, because instead of the K that you select first, you end up with whatever number of units you need to end up with contiguous entities. And if you're going to keep the K but then manually reshuffle units, that is also becomes impractical very quickly for larger data sets. In our little Gary example, we have, just to keep it simple, on the left, a k-means with k equal 4 solution. And as we can see, this blue one is kind of sort of contiguous here, but then there's a unit over there. The light blue one, same thing. So one thing we could do is make each of these separate grouped entities a separate cluster. So then we end up with the situation on the right where we have 12 clusters, so that each entity from the right that was unconnected becomes its own separate cluster. And most of these end up being singletons, except for this one, which is a grouping of 4 entities. But you see that this very quickly becomes kind of unwieldy, and most importantly, we end up with a lot of singletons, which is not very useful. So the singletons are these entities that are by themselves, like this region here. This department really belongs to this group in terms of attribute similarity, as well as do these. So they are nowhere near geographically connected. So then you start splitting them, and for all practical, it's nice as kind of an illustration of what the problem is, but for all practical purposes, it's not really useful. Then the other approach, as I mentioned, will only work for smallish toy problems. So in this case, what we're doing is kind of ad hoc connecting things. So we make this department part of this green group, and then connect them this way, and then connect them this way. So then we have one big green connected cluster. With the dark blue cluster, we just switch these to light blue and then connect this way, and again we're in business. And then with the light green ones, we just switch this one around, and then we have 4 contiguous clusters. Now, what is the problem with this? The problem is that's purely ad hoc. We have no way of knowing whether this is actually an optimal way of swapping out entities, and for really large problems, this is impossible to do. So instead, before we go into the explicit spatial methods, there are a couple of, as I mentioned, tricks to nudge or force classic cluster solutions towards contiguity. So these are what I call soft spatial constraints, in that they move the solution towards contiguity, but they don't, except for the last one, ensure contiguity. So we will see 3 methods: clustering on coordinates, which is very straightforward, including the coordinates among the features in the cluster exercise, which is a very commonly applied method. And then a final one is kind of, I think, pretty unique to GeoDa, to the implementation in GeoDa. The idea of weighted optimization is not unique, but the assurance of contiguity in the process is something that GeoDa achieves. So let's look at them one by one so we get a sense of what this does. So first, clustering on the coordinates. Nothing new there. We've actually done this several times already. In fact, every one of the toy examples was a clustering on coordinates. So straightforward application of classic methods. Only coordinates as attributes, no other coordinates. One thing to keep in mind, first of all, the coordinates need to be projected, because the notion of Euclidean distance, which underlines, or Manhattan distance for that matter, which is underlying every one of the classic cluster methods, only applies to points in a flat space only applies when Euclidean distance is appropriate. Latitude and longitude are not appropriate. You will see this in the literature, unfortunately, but latitude and longitude are out. You always need to project. The other thing to keep in mind is that if you apply the cluster exercise to the XY coordinates only, it's best not to standardize them. And why is that? Because the standardization turns everything into units of standard deviation. But in a squarish region, like the French example, that doesn't really make that much of a difference. But if you have a long stretched out region like Chicago or California or Chile, then the distance range in one dimension, in one direction, is much larger than in the other dimension. So one standard deviational unit in one dimension will be a much larger distance than one standard deviational unit in the smaller dimension. So in other words, by standardizing, we make the X and Y distances not comparable anymore, and they really should get the same weight. So it's better not to transform the coordinates, and the result is compact regions. As we've already seen in the context of k-means, the result is actually the same as Thiessen polygons. And just to give you an idea what this looks like, there's really no point into going into too much detail, is that this is an example of k-means here on the upper left, k-medoids, spectral clustering and hierarchical clustering using Ward's criterion. As we've already seen, the results are not the same. This uses a point pattern of abandoned vehicles in Chicago. The results are not the same. The differences are fairly subtle. The clearest one is the k-means, where you see that the boundaries between the regions are actually match Thiessen polygons between the centers of the regions. And so this is k-medoids. That is the application of a solution to a location allocation problem, as I mentioned in the previous lecture. And so anytime you need to find, say, then you find the medoid will be the central point in each of these regions, and that would be, say, the warehouse from which you supply the other warehouses, as an example. So anyway, you get the idea. Clustering on coordinates is solving a location problem. Do not transform the coordinates and make sure that they are projected. The second approach is bringing the coordinates among the features, and that's also an old method. Here, unfortunately, because the attributes are typically standardized to keep them comparable, the X and Y coordinates will also be standardized. So this, as I just mentioned, distorts the relative distances in the north, south, and east-west directions. And depending on the shape of your problem, this could be an issue, an important issue. The other thing to keep in mind is that since the X and Y coordinates are included among the other variables, just like any other variable, every variable gets the same weight. So if we have p variables, each variable gets a weight of 1 over p, so to speak. What this implies is that if we have many attributes, many regular attributes, the effect of introducing 2 more in the form of X and Y is going to be minor. On the other hand, if we have only a few attributes, like in our examples, then the effect of introducing X and Y can actually help. This is an example of a soft spatial constraint in that it nudges the solution towards the centroids of the X and Y coordinates for the clusters, but it doesn't force them to be contiguous. So to illustrate this again, 4 examples: k-means, k-medoids, spectral clustering, and hierarchical clustering. 4 clusters, standard, no spatial constraints whatsoever. This, again, just to reiterate, gives you a sense of how the solutions can vary depending on the method that you use. So it's very important, depending on the objective of your study, that you don't stick to one method only, but look and assess the extent to which the solution changes when you change the methods, and also when you change the parameters in each specific method. Okay, now we take the same 6 variables and we add x and y. What happens? In some methods, it works better than for others. And we see, for example, that these the previous regions, which were kind of cut up in pieces, become much more grouped. Much more grouped for some clusters, more so than for other clusters. So, for example, here, for k-medoids, the solution is spatially contiguous, except for this one here in cluster 3, and these two not being connected in cluster 2. In hierarchical clustering, we get a similar solution with the cluster 4 missing 2 pieces and cluster 1 missing 1 piece. But the others, you can see the effect of the x and y is to pull them closer together and forming a more compact region, but there is no guarantee of contiguity. In contrast, in the third method, the weighted optimization, we actually force contiguity. So here, the weighted optimization is just a special case of weighted clustering. You can have different weights for the different variables. We haven't really addressed this in our discussion because we always standardized all the variables and gave them, equal weight in the process, but you don't have to do that. You can give more weight to some variables to some extent. That becomes arbitrary, but in this case, it isn't, because what we're going to do is give weights to the regular attributes and weights to the spatial coordinates. Let's say we give the weight W1 to x and y, and the weight W2 to everything else. So, in a sense, what this boils down to is that x and y each get half the weight, and then each of the attributes gets the weight divided by p. And of course, these two weights, W1 and W2, add up to 1. So let's say W1 can be 0.4, then W2 is 0.6. We have x and y, so the 0.4 becomes 0.2 and 0.2 for x and y, and the 0.6 becomes 0.1 for each of these 6 attributes. That's the weighting part. Now, in addition to this weighting, we have a check on contiguity, and we can do that in GeoDa because we have a dynamic updating of the weights, and that's too technical to discuss here. If you're interested, it's explained in more detail in the lab notes. But in essence, what it means is that we can check on the fly whether the solution that we obtain in terms of the clusters, it's actually spatially contiguous or not. And now we use this in an optimization process. So specifically, we're going to use a very simple optimization method for one parameter, and that's called a bisection search. Bisection because you cut the interval into 2 each time. So we start with full weight to the coordinates, which is a purely geographic solution. That's exactly the same solution as we had in the first of the 3 methods where we cluster on x and y. So we start with that. That's the point of departure. And then we drop the weights to the midpoint between 0 and 1, which is half, and we check on contiguity. If the solution is contiguous, we cut the weight in half again. We move to 0.25. If it is not contiguous, then that means that in order to get contiguity, we have to give a higher weight, a larger weight to the coordinates. So then we move up. So every time we cut the remaining interval into 2, if we have contiguity satisfied, we make the weight for x and y smaller. If we don't have it satisfied, then we make the weight for x and y larger. So by doing this, we can move towards the solution that has the smallest weight for x and y, and therefore the largest weight for the actual attributes, and satisfies contiguity. Now, the bad news is that this doesn't always work. And there are, in fact, situations where you cannot find a solution for the given k that satisfies contiguity. So then you end up with a weight of 1, and in essence, you ignore the attributes, which is not what you want. And so to illustrate this, again, using the Gary example, we start with the weight of 1. We have contiguity. We go to 0.5. So we decrease the weight by half to get this one. We have contiguity. We decrease the weight by half to get this one. We don't have contiguity. Then we have to increase the weight to get 0.375. So no contiguity. We keep increasing the weight. We keep increasing the weight till we hit 0.484, where we satisfy contiguity. Now we can decrease the weight again. Now we don't satisfy. We go up again. We go down again. And we keep doing this till the change becomes small enough that we can ignore it. And at that point, we look what our solution is. And so the good news is we have guaranteed contiguity if it is feasible. If it is not feasible, of course, we can't force it. And then we end up with a solution that is, in fact, contiguous, but is not very meaningful in terms of the attributes, because the attributes don't get any weight. So that is something to keep an eye out for. So don't do this just mechanically. It's only really meaningful if you can establish a weight for the xy coordinates that is small enough so that it gives enough weight to the non-spatial coordinates to the actual attributes. So that's a very easy and straightforward way to assure contiguity, so to enforce the spatial constraint, but we use all the classic methods. And this can be applied to any one of the methods, and here's an illustration of what it looks like. The best solution, quote unquote, is the one we obtained for k-medoids, where the weight is the smallest. For example, for spectral clustering, the result is not very good at all. Even though we obtain contiguity, we have to give a much higher weight to the coordinates. So this weighted optimization, this was suggested a long time ago as a possible solution, but at that time the contiguity was not enforced mechanically. We can apply this to very large problems, and the check on the contiguity doesn't have to be based on visual inspection, which is historically what happened, but can be become part of the optimization routine. So this, in a nutshell, kind of gets us going into thinking about how the spatial constraint, making sure that the clusters that we obtain are spatially contiguous, can be brought into the optimization process. And in the next 2 lectures, we'll look at specific methods that embody this in hierarchical clustering and partitioning clustering. See you then.